Hey, good morning, team. Chemistry coach coming at you. You ready to practice some of those gas laws we derived in the last video? I hope so. So instead of going, what's commonly done, people, somebody will introduce a gas law to you. This is Boyle's law. Let's do a problem. This is the ideal gas problem equation, the perfect equation. Let's do a problem. This is the general gas equation. Let's do a problem. I kind of just flipped it around and said, hey, let's show you where all these gas laws come from. Here's the PV equals nRT. Here's the general gas equation. Boom! We can derive every other equation from it. I would practice that actually. You're bored on a date at Saturday night at some restaurant saying, you're so boring. And, pull out a napkin, draw a circle in there, put PV equals nRT, and draw all the other circles like that wheel that I did for all the gas laws, and then try to algebraically derive all of them. And say, this is more exciting than you stupid date. All right? Whatever works. Or you're sitting on the toilet, for a long period of time, grab some toilet paper, practice it. Whatever. You're stuck at a stoplight or something or in traffic. Practice. That's what I did. I just practice. I really encourage you to learn how to derive things, do algebraic substitutions, and know where equations come from rather than just memorizing them. Right? You can memorize them, but sooner or later they probably will leak out of your brain. But if you can just remember PV equals nRT, you can derive all of them from that. You can do it. Yes. So now, we didn't do any mathematics in the last video. I just introduced all of those different gas equations. Remember, that's all assuming ideal gas behavior. When we're not assuming ideal gas behavior, the whole game changes. Let's do some problems like you would see on a test. On an exam or a quiz, I'm not going to sit here and say, this is a general gas equation problem. Use the combined gas law for this. This is a Boyle's law problem. I'm not going to tell you that. I'm just going to say, here's some data. You got to figure out which of those equations to use, right? So I'm just going to throw, 3-4 different problems on here until we run out of time. I don't like going over half an hour on these videos. That way you can go take a potty break or a lunch break or something. This is something you might see on an exam. And I want to go more into how to think about it, right? Once you set up the equation, anybody can throw the math at it. Anybody can take their calculator and go, even though I usually fat finger syndrome, blah, blah, blah. Yeah, I screwed it up again. But once it's set up, most people, if given enough time, can get the numbers in the calculator. It's straightforward. But we got to try. I want you to track these units. I want you to think about why you're using whatever equation it is. Sometimes you could take 2 or 3 different approaches. That's okay. It might be a little longer, but you still get there. Whatever works. But let's say we got this situation. What's the pressure exerted by 3.2 times 10 to the 22nd helium atoms? In an 800, in 840, in an 845, in 800. English was not my best class. Milliliter container at 24.1 degrees Celsius. Trying to figure out if that's an A or an N. In an 8, in an 8, in 8, in an. I love math so much better. Math is so logical. All right, here we go. I always like to think about what am I solving for, right? What information do I have? Because there can get a lot, especially if you're doing the general gas equation or something. You got 7 different variables. You're like, there's so much changing conditions. I like to figure out if I have static or non-changing conditions, or if I have changing conditions. So I'm looking for 2 pressures, 2 temperatures, 2 different volumes, something like that. So I'm just going to list out my information here and see what the sign says. So it says, what is the pressure? Obviously, I'm solving for the pressure. That's my key. Probably going to be a gas law problem. That's how you recognize that. I've got atoms. So that's not anything in PV equals nRT directly. I've got a volume here, right? I got a volume. I got 845 milliliters. I've got a temperature. Now, would you agree I need that temperature in degrees from degrees Celsius to Kelvin? Let's convert that to Kelvin because R, the gas constant's as Kelvin. So let's add 273.15 to that. This is exact, so you're limited to the 1 decimal place. So get out your trusty dusty calculator. I like to do this. I don't require you to show that work, but a lot of students who don't show it sometimes screw up their significant digits. Their uncertainty gets messed up because sometimes the temperature will limit you. 24.1 plus 273.15, 297.25. Good to 1 decimal place. All right, so we got our temperature there. Now, some people like to convert milliliters to liters knowing that's going to be necessary. I don't like to do that. I don't like to anticipate what units they need to be. I'm just going to throw them into PV, into the equation I need, and then convert units as necessary when I do the dimensional analysis or the unit line equation, right? So I got P, I got V. Do you see another pressure? I don't see another pressure. I don't see another volume. I don't see another temperature. So this looks like static conditions, right? So this is static conditions. That means no change, right? No changes. So we're going to use PV equals nRT. So I've identified the equation I need, right? So let's take a look here. We got volume, right? I know volume. R is a constant. I'm given T. I have T, I have V. I'm solving for P, which means I only need N, which I can get from the atoms. Yes, I can. So then what we'll have to do is convert number of atoms to moles. That's our N. Now you can do that in one step in the unit line equation, or you can do that separately. I'll do it separately just so we can see what's rocking on the next page. But this is stuff I kind of usually just do in my head. I don't normally write this down when I'm solving a problem. But if you're stuck, just list out your data, right? Solving for that, I got this, I got this. I don't have a second volume or temperature or pressure, so this is just the pervert equation, ideal gas equation. So we're going to rearrange this, isolate your variable, P. I like you to do that. So do that for me. Pause it, isolate P. P will be nRT over V. If you want to convert your number of atoms of helium to moles before that and then plug it in, go for it. But try to do it in a unit line equation for me. I'll erase this and we'll work through the problem. All right, did you solve for moles or are you going to wait to do it later? I actually usually don't do it this way. I usually just plug all my information in and do it in one line equation. But I do have limited space on my board. I'll run out of space before you do on your paper. I'll be like, cliff on the end of the board. So let's take the number of atoms provided of helium, and really the identity of the gas doesn't matter at this point. We got 3.2 times 10 to the 22nd. That's a lot of atoms. Remember, if we're going number of particles to moles, you want, I keep wanting to say Avogadro's number, 6.022 times 10 to the 23rd atoms. I would provide you that. I give you Avogadro's constant on exams. You probably already have it memorized. Per mole. I'm stuck to the two significant digits here, so I get 0.05313 moles of helium. Good to two significant figures. So now let's take our equation. We know that PV is nRT. That's our ideal gas law, assuming the particles of the gases are tiny compared to the container, and then there's no interactions other than direct collisions. We're solving for the pressure, correct? So isolate your variable. Divide both sides by V. So the pressure will be nRT over V. Please isolate your variable. I want to see that step. Because if you don't show it, somebody reading it may not know what you did, or you're forcing them to do the algebra. And people get irritated when they're forced to do algebra when they shouldn't have to. Be super clear. And it prevents mistakes. All right, this will save you from some mistakes. You try to do it in your head sometimes in a rush on a test, you get it upside down. So let's plug in our moles right there. So 0.05313 moles. We don't even necessarily need to put the helium there. Let's divide that by the volume. What was our volume? Let's look at our problem. Tell me what the volume was. Was that 845 milliliters? Was it? Let's multiply by the universal gas constant, which I'll provide you. Now set it up as a unit line equation. You've got in R, you've got numerator units and denominator units. So set it up as a dimensional analysis problem, right? So we're multiplying by R. So 0.082057 liters times atmospheres per mole Kelvin. So let's take a look at some units here. See the moles cancel out? Now the problem with this is the milliliters do not cancel out. Even with this, I'm not going to be able to fit it on the board. So because I'm in milliliters, now some people prefer to convert milliliters to liters ahead of time and then stick it in there. I don't like to anticipate that ahead of time. So I'm just going to do another connector and convert my milliliters to liters. So milliliters are in the denominator here, so I'm going to put them in the numerator there. 1,000 milliliters per liter. And that allows me to cancel out milliliters and liters. Now remember, we're solving for pressure. So we want, now it didn't specify the units of pressure. Yay! So just leave them in atmospheres. It didn't say in bars or in kilopascals or pounds per square inch or something. If we did, we just add one more step and convert atmospheres to whatever pressure units we're after. But atmosphere is by far the most common unit you're going to see in an undergraduate chemistry class. Now, out in the real world, like I said, PSI, those kinds of things, that's going to be a little more common. And the IUPAC's pushing us to get towards bars or towards more SI units like pascals. Nobody likes pascals. I'm not done. Do you see the Kelvin dangling there? So on your paper, just add one more step here. So we need to multiply. Obviously, see, Kelvin's in the denominator, so does it make sense we have to multiply by the temperature? I ran out of room. Well, even if I had a longer board, it wouldn't fit on my screen. The limitations of remote teaching. Let's see. And I like to do this live, right? Rather than on a PowerPoint or something. I want you to watch me think through the problem. The key is learning how, not just regurgitating what the teachers do. It's like learning how to solve it. How do you think on a test? Because I ain't going to be, putting baby powder on you and changing your diapers on an exam, right? I'm not going to let you phone a friend. You're on your own, so you need to practice how to think. So I take my time. I do fewer problems, but I like to think about them and show you my brain in real time. All right, so what was our temperature? 297.25 Kelvin. 297.2. Good to 1 decimal place. And so here, now if you want to put over 1, you're welcome to. You don't need to. That's not necessary. But if you like the spacing of that, that's great. So Kelvin in the denominator, numerator, I'm left with just atmospheres. So I found a lot of students just want to do gas law problems like a mathematician. And the numbers work, but a lot of times you get things upside down because you lose track of the units. You don't realize you should have been in bars instead of atmospheres, or I gave you millimeters mercury, you should have converted to atmospheres, or you didn't convert the temperature properly. They lose track of the units. A chemist thinks in terms of units, and then the numbers just fall into place. All right, it's a little bit different. So I'm trying to get you to think in terms of the units. So if I do this, I have 2 significant digits in my moles, 3 in my volume, 5 in R, that's exact, 4 there. So I'm limited to the 2 significant figures from the original number of molecules. And if I had done this on my own, I would have started with the molecules here and just added another step here. I would have just inserted this right there. Totally fine. I don't care. Not a big deal. All right, so what do you get? I get 1.533 atmospheres. Good to 2 sig figs. So that's closer to 1.5 than 1.6, so that does not round up. That would be the pressure exerted by that many helium atoms under the stated conditions of pressure and temperature, because it's dependent on the volume and the temperature, right? There you go. That's how you do an ideal gas equation problem. Not a big deal. Right? I could have flipped it and given you P and have you solve for V, or given you everything else and solve for T. It's the same. Just isolate your variable, plug it in, watch your units, you're off to the races. Boom! Let's do another one. Next problem. At 32.5 degrees Celsius, a balloon has a volume of 1.87 liter. Okay, we got some stated conditions. What is the volume? Oh, wait a minute. Going to be a volume change. We can't use the PV equals nRT. We can't use the ideal gas equation here. What's the volume when heated to 86.2 degrees Celsius? So we've got a change in temperature and a change in volume. There's nothing specified about the pressure in moles. Now, you can probably bypass this step, but this is changing conditions. Everybody agree? So I'll do my thinking and then solving on the next page. Changing conditions. So if it's changing conditions, let's put the general gas equation, right? So P1V1 over N1T1 equals P2V2 over N2T2. But if nothing is stated about if I don't give you N1 or N2, we have to assume they're constant. All right, so we're going to make some assumptions here. I'll do this in green. Since it's not stated, assume N and P are constant. They are not stated in the equation. Therefore, N1 equals N2, so they're going to drop out, and P1 equals P2. This is what I do in my head. If that's the case, then N1 drops out, P drops out, so we get V1 over T1 equals V2 over T2, and that is Charles' law. Right? So when the pressure in moles are constant, you end up with Charles' law, the hot air balloon Frenchman, back in the late 1700s. Now, if you'd memorized that, you could have recognized it and just gone straight to that. But I'm showing you, if you're stuck on a test, you don't have the equations memorized, you forget them. Just go, you understand, if it's non-changing conditions, P equals nRT. If it's changing conditions, do the general gas equation, which you could derive from P equals nRT. I showed you how to do that in the last video. And then say, okay, then go, well, what is constant? That will drop out of the equation. It leaves me one of the simple gas laws. A simple gas law is just a derivative of that with something being constant. All right? So let's do this. What do we know? What do we know? We know the initial temperature. I know the initial volume, right? V1 and T1 are given. I'm given the final temperature. We're going to solve for V2. So I'm going to isolate V2. So I'm going to multiply T2 to the other side. We're good to go. Let's solve it on the next page. See if you can do it before I'm done, right? Isolate your variable, plug in your stuff. But watch out. Your temperatures must be in Kelvin. Degree Celsius cancels out, but what if you had like a negative, I could have easily had like a negative 25 degrees Celsius to start with, right? Well, that would end up giving me a negative V2. That doesn't make sense. Or if I put a 0 here or something, you could get a volume of 0 or a volume of infinity. That doesn't make sense either. So they must be in Kelvin. So convert your temperature, both T1 and T2 to Kelvin first, then isolate your variable, and then solve for it. I'll do that on the next board. See if you can do it before I do. Ready, set, go. Did you finish? Did you finish? So T1, 32.5 degrees Celsius. Add the 273.15. That's exact, limited to one decimal, because we're adding, limited by largest absolute certainty, or fewest decimals. I get 305.650 Kelvin, good to one decimal place. For T2, it's 86.2 degrees Celsius. I do the exact same thing. I add 273.15 to convert to Kelvin, right? Because remember, a Kelvin and a degree Celsius are the same size. If you look back at the temperature video, it's just that the freezing point of water is off by 273.15, so we have to account for that reference point. So good to one decimal, I get 359.350 Kelvin, good to one decimal. And we're using Charles' law, so let's isolate our variable, right? We're solving for the final volume at a higher temperature. Now, let's think about it. Volume and temperature are proportional, right? You increase the temperature, you increase the speed, right? And so the impulse they provide when they collide is higher, and the collision frequency is higher. To maintain a constant pressure, because pressure is going to increase based on the definition of pressure. So to keep pressure constant, the volume has to expand to account for it's trying to counteract the increase in pressure, right? From kinetic. I always like to think in terms of kinetic molecular theory. So at the higher temperature, the volume should go up, right? So make sure you understand that, right? I should get a higher volume than I started with. So V2 will be V1 T2 over T1, right? So I'm just multiplying both sides by T2. That's all I'm doing. So what was our original volume? What was that, 1.87 liters? Now in the problem, it just says what's the volume. It didn't specify the units again, right? So just leave it in volumes, right? If I asked for quarts or something weird like that, you could convert it, solve for liters, and then convert it to whatever you need. What is T2? That is right here. 359.3 Now here, when you're using the simple gas laws like this, Boyle's law, Avogadro's law, Charles' law, you don't need to do dimensional analysis because there's really no unit conversions. You're just canceling out. I'm going to cancel out Kelvin and be left with liters. Let's put T1 on the bottom, 305.6. You don't have to put parentheses around the numbers. Can you see the Kelvin cancel? Boop, boop. I'm left with liters, and since it wasn't specified in the problem, I'm just going to leave it as liters. I'm doing all division multiplication, 3 sig figs, 4 sig figs, 4 sig figs, so I'm limited by the fewest or 3 significant digits. So I get 2.19 vertical dash line, that's my 3 sig figs, 2.1985 liters. So that's going to round up, right? It's closer to 2.20 than it is to 2.19. Is that larger than the original volume? It is! Makes sense, right? Please isolate your variables, isolate your variables, isolate your variables. Let's do a harder one. Hopefully you can't hear my children's virtual piano recital through the video, but if you can, enjoy the Star Wars theme. No, E.T.? Is it E.T. or Star Wars? I can't remember. They're not playing it quite right yet. It's still practice. So what is the mass of 2.27 liters of nitrogen gas at 25.0 degrees Celsius and 771.4 millimeters mercury, which you should understand is a pressure. Now, what do we got here? We've got a temperature. Obviously, we're going to have to convert that to Kelvin. Can we go ahead and just start with that? So temperature is 25.0 degrees Celsius. That's a tiny C. So what's that going to be? 298.15? Is that right? Good to 1 decimal place. 298.15. Yeah, limited to that 25.0. That 0.0 counts. Trailing 0 with a decimal. What else am I given? I know my pressure. 771.4. We're probably going to have to convert that to atmospheres, but I don't like to anticipate that. I'll do that in the unit line equation later. I know the volume. That's good. I got PV. I've got the mass. So there's 2 ways you can do this problem. You could take the mass. No, I'm solving for the mass. So you could solve for moles. You could use P. So non-changing conditions. You could use PV equals nRT, solve for N, and then convert the moles to grams using the molar mass of nitrogen. Or you can understand one of the gas equations we derived on the other video has mass in it. So if you remember, PV's nRT, but moles is mass over molar mass. If you remember that. So if you plug that in there and do the algebraic substitution, PV is mass over molar mass times RT. See where mass comes into play? So mass, what we can do, we can just use this equation and then isolate mass. So the mass will be PV times molar mass, is that right? PV divided by RT. See if I do my algebra correctly here. So we isolated that in there. We're solving for mass. So PV, multiply through by the molar mass, divide through by RT. All right? And then we know the pressure. Correct? We know the volume. Do you know the molar mass of nitrogen? Yeah, it's 14.0067 times 2. R is a constant. I know my temperature. Solve for mass. Give it a shot. Obviously, I have no room. Let's do it on the next board. Go ahead and see what you get ahead of time. Track your sig figs for me. All right, let's walk it through. So we've isolated our variable. Let's plug everything in. Pressure, 771.4 millimeters mercury. Let's times that by the volume, or you can either times by volume or divide by R. It doesn't really matter. Have some fun. Let's divide by R. So 0.082057 liters atmospheres per mole Kelvin. Right? So P's done, R's done. Do you see how the units don't work out? We got millimeters mercury there and atmospheres there. Some people like to convert that ahead of time. That's fine. So let's go ahead and do that here. I want to get rid of millimeters mercury. And I want atmospheres on the top. That's a 760 to 1, right? And therefore I can cancel. Let's use green. Let's cancel out my millimeters mercury and my atmospheres go bye-bye. I'm solving for mass, so this will come into play when we put my molar mass in. I've run out of room, so let's continue this unit line. See if you can do it all in one line on your page. So we did pressure divided by the universal gas constant, converted our units. Let's do volume. What was that? 2.27? 2.27 liters. Now, liters is in the numerator here and denominator there. So liters cancels out. If I'd given you milliliters, we'd have to convert milliliters to liters. Let's multiply by the molar mass. So let's take 14.0067. That's nitrogen, right? 14.0067. And I get 28.0134. Grams of nitrogen per mole. Do you see moles in the denominator? Moles in the numerator. Ho ho! And we got grams, we got mass. And it didn't specify, you know, milligrams or megatons or whatever. So we've done V, we've done M. We just got to get the temperature in there. Do you see that? It needs to cancel out. So let's divide by the temperature. Now you can either put the temperature down here, or you could go like this. 1 over the temperature. That's one way to divide by something where there's nothing in the numerator. Just go 1 over that. Like this is technically over 1, correct? So this is how you flip that uniline equation. So what was our temperature? 298.15, right? Do you see the Kelvin in the numerator? Kelvin in the denominator? Every unit cancels out except for grams of nitrogen. Feeling pretty good. So I got 4 sig figs, 5, that's exact. 3, a lot. 4, so I'm limited to 3 significant figures. So what do you get? I get 2.6381 grams of nitrogen. That's going to round up to 2.64. Wada bing, wada boom, right? Not too bad. Let's do one more, and I'll do it fast, and we'll be good to go. All right, here's another one. I'm showing you how to look for keywords. The last problem, the keyword was the mass. Remember, that's the only gas law equation that had the mass in there, with the molar mass and mass. So what is the density, or my density, of carbon monoxide gas at 0 degrees Celsius and a pressure of 1.00 atmospheres? Those are going to be important in the next video. We're going to look at something called standard temperature and pressure, kind of a reference point. But notice the word density. There's only one gas law equation that has density in it. See if you can go find it. I'm going to rederive it for you, but see if you can go find it or if you've memorized it. So I'll write it up and derive it again real quick. All right, remember the derivation? So we got P equals nRT, but moles is mass over molar mass. So insert that in there. That gives you the molar mass equation, right, that we used in the last problem. But I just rearranged it. So what I did is I moved volume to the other side. So let's divide volume by both sides. So pressure would be mass times R times T divided by molar mass divided by volume. I just moved the mass. Now what I did is I isolated mass over volume and RT over molar mass like we did. This is in the last video. Mass over volume is density, so I'm going to insert density in there. So density times R times temperature divided by molar mass equals pressure. Let's isolate density. So multiply through by molar mass, divide through by RT. So density is the pressure times the molar mass divided by RT. Hey, now plug your numbers in there. You know the pressure is 1 atmosphere. Molar mass of carbon monoxide, 12.011 plus 15.9994. R, you know that. Temperature, convert that to Kelvin. Do it. See if you get what I get. Let me erase this board. All right, we got our, so convert your temperature to Kelvin. Now there's an issue here. Is that 0.00? Is it 0 exact? It's not specified. Since there's no decimal places there, it's kind of weird on the uncertainty. So I'm just going to assume that's exact, right? And go 273.15 for my temperature. So here's our equation. Let's put our pressure in, 1.00 atmospheres. Molar mass, 12.011 plus 15.9994. Go to 3 decimal places. I get 28.01040. Go to 3 decimal places. Grams per mole, carbon monoxide. Let's divide by the universal gas constant, 0.082057 liters times atmospheres per mole Kelvin. Remember, that's how you divide something in dimensional analysis. And I wanted to divide by temperature. I ran out of room. Normally, I'd go 1 over 273.15 Kelvin, but you can really stick it anywhere in the equation. So I just put it here. So I did pressure over temperature times molar mass divided by R. Let's look at our units. Atmospheres in the denominator and numerator. Kelvin in the denominator and numerator. Moles cancels. Leaves me with grams per liter, which, if you remember with gases, those are the units for densities of gases. Hey! Grams per liter. Liquids, grams per milliliter. Solids, grams per centimeter cubed. 3 sig figs, we're assuming that's exact. 5, so we're limited to the 3 significant figures. So let's pop this out, and I get 1.24 vertical dash line, 96 grams per liter, right? Grams over liter. That's going to round up to 1.25. Or you could go grams times liters to the -1. Boom! 4 all-encompassing gas. I didn't get them all. I wasn't going to do 9 different problems, but you got 4 and kind of showed you how to set them up and think about them and stuff. I think you're going to be okay.